So taking a look at our bell work, in this case, we are being asked to figure out all of the zeros of our x cubed minus 43x plus 42. Now I could have given this in a couple of different ways. I could have said when we know that 1 is a 0. I could have said that when we know that x minus 1 is a factor, ultimately both of those are the same fact, but this idea that x minus 1 divides evenly kind of into our polynomial here. All right. So first of all, just kind of looking at this equation, when we are given a cubic, do we have just with the cubic alone a really good way to find its zeros? Not really. No, right? We established that yes, in fact, there is a cubic formula, just like with a quadratic formula, and it's horrible and disgusting and evil, and we never want to have to use that ever. And so instead, what we need to do is we need to take this cubic and try to reduce it down to a quadratic that we can actually work with. Because as bad as the quadratic function is, the cubic function is like 1,000 times worse. So we're just going to try and stay clear of that as far as we can. All right. And so how are we going to reduce the degree from cubic to quadratic? Well, we're not really going to reduce the degree, but what we are going to do is divide out this x minus 1, and hopefully we'll be left with, and not hopefully, but we will, in fact, be left with, at the end of this, a quadratic function. So taking this x minus 1, dividing it into our, now x cubed, what do I have to remember to include here? Plus 0x squared, very good, minus 43x plus 42. And then we're just doing our long division process. So trying to match x to x cubed. What do I have to multiply by? X squared. So I get x squared, x cubed rather, minus x squared. We are subtracting. X cubed minus x cubed is 0. 0 minus negative x squared is going to be positive x squared, very good, minus 43x plus 42. How do I match x to x squared? With an x. So this gives me x squared minus x. We are subtracting. Again, at the front, we get 0, should always get 0. Negative 43x minus negative x is going to be negative 42x. Very good. And then how do I match x to negative 42x? With a negative 42. And again, subtracting these, and we get a remainder of 0, which is good. If this was a remainder other than 0, then x minus 1 either wouldn't be a factor, or we made a mistake somewhere along the way and we'd have to go all the way back. Rather annoying and not very fun. Okay, so that's great and all, but again, this is just kind of information that we already knew. If we know that x minus 1 is a factor, then we'd expect the remainder to be 0. What we have gained from that is not the fact that the remainder is 0, but is instead this other piece, this thing that we are left with after we do the division, which allows us to write this cubic as x minus 1 times what we got here, this x squared plus x minus 42. Which is considerable progress because now we have a quadratic that we can either factor using the quadratic formula, or maybe this one would be a little bit easier to just do by our normal factoring process. So looking at this quadratic, what are two numbers that multiply to make negative 42, that add to make positive 1? 7 and negative 6, very good. And so taking this, we do our factoring process. You can split apart the 1 into a 7x and a negative 6x, blah, blah, blah. You should, with a little bit of work, get that x minus 1, that this function is x minus 1 times x plus 7 times x minus 6. Yeah.
Isn't this just like the division algorithm?
Yeah, this is just the division algorithm.
Different name?
Well, yeah, so we're using the division algorithm in order to factor a trinomial, or not trinomial, but a cubic. Yeah.
So what's the division algorithm versus the remainder theorem?
The division algorithm is like a piece of the remainder theorem. It's like a part. It's something that the remainder theorem uses. Yeah. The remainder theorem uses the. This is the factor theorem, which also uses the division algorithm in order to kind of make the claims that it makes. Yeah. So it is the division algorithm. Well, all we're doing is the division algorithm. All of the conclusions that we come to are because of the division algorithm. In fact, we don't even really need to mention the factor theorem. It's just the name of the thing that says that we can do this. Okay, so what are our 3 zeros here? 1, -7, and 6. Very good. So I gave us that 1 was going to be 1, but then finding the 2 missing in this case, -7 and 6. So this ends up actually being a fairly powerful tool because really we didn't have good, consistent, reliable ways to deal with these kind of cubic polynomials before. Now, if I give you a cubic and one of the zeros, we have this ability to find all the others. And we could extend this to, like, if I gave you a 4th degree polynomial and 2 of the zeros, then you could certainly divide down in order to find the rest. If I gave you a 5th degree polynomial, down until you got down to a quadratic. The unfortunate thing, though, is that this still isn't fully self-sufficient, right? If I had just given you find the zeros of x cubed minus 43x plus 42, we're still a little bit floundering. We don't have super great reliable ways to find this from scratch. I needed to accompany it with this kind of kernel of information here that x minus 1 is a factor. So ultimately what we're going to be working on today is that self-sufficiency. If I just gave you this x cubed minus 43x plus 42, how could we try to tackle finding the zeros, or at least like where would we look to start? Where would we begin? Before we take a look at that, though, I do want to make one quick mention. And that is there are a couple of problems on the classwork that ask you or that give you this kind of information, but the zeros that they give are maybe a little bit trickier than, say, like 1 being the 0. So I want to just kind of think about, if I were to tell you that 2/5 is a 0, and I wanted to write a root that kind of goes with this 2/5. There's one that's like very, very quick and easy to come up with that's just based on the factor theorem. If this is a 0, then that means that this must divide my polynomial. But then there's another one that's maybe a little bit more clever that can keep the numbers from getting kind of gross as we work. So looking at this, just kind of write really quickly, purely using the factor theorem, what is the root that we would get from the fact that 2/5 is a 0? Pin in that one. Even more simple than that, actually, because that is ultimately what we are pushing towards. X minus 2/5 is kind of what we were like starting with. And this is certainly true, that this would, in fact, be a factor. Problem here, though, is we're going to be working with this 2/5 fraction while we do the division. That's a lot of room for error. That's a lot of kind of place to make some kind of mistake that can carry throughout our entire kind of equation. And so Surya's idea here of instead writing this as 5x minus 2 is a really good one. Notice that 2/5 makes both of these zeros. And if that's the case, I should be able to use either one as my root. This one technically divides our polynomial by 5 more than the other one, but that's okay. That doesn't really change anything. We would see that 5 show up somewhere else in our polynomial anyway. And so either of these are totally fine. Both of those are completely fine. I just wanted us to kind of see that, yeah, we could do this x minus 2/5, but there are generally kind of not better workarounds, but there are other workarounds that would allow us to kind of tackle this, to kind of deal with it. Okay. So for the sake of self-sufficiency, we are going to be looking at what is possibly, in my opinion, one of the trickier theorems that we're going to be dealing with. The good news is that the math isn't like super horrible with it. But there are a lot of moving parts. There are a lot of letters. The certain letters have like some associations with certain parts of our function. I think it can be a little bit hard to just kind of keep track of in a very generic sense. So what I'm going to do, we are going to do kind of for the first little bit here, is not to prove that this theorem is true. What I want to do is kind of give you like a skeletal outline of some of the logic that goes into these conclusions that we're making, so that hopefully you can, even if like you don't brute force memorize this, kind of come to some of these connections yourself, and kind of make some of these associations that we're going to make. So what we're going to be doing, again, our goal, given just this kind of polynomial where we don't have any of the useful information, to take all of these useful numbers that don't really tell us anything and to turn them into the zeros. So to take our polynomial, to write it out as a product of all of its zeros. To show this, we're going to do the opposite. We're going to start with the useful information, and we're going to see how does the useful information transform into the useless information. Right. So let's start with an example here. We'll look at 2 times x plus 3 times x plus 4. Actually, here, better yet, let's look at x minus 4 here. Just kind of drive our point across. If I'm trying to take this from the useful form, where it's like factored and all nice, and turn it into the more useless form, I would do out the multiplication here. So you could do the Punnett square or what have you, whatever you want. This is going to end up being, FOIL it, probably being the other one. This is going to be x squared minus x minus 12, and then distributing this 2, I get 2x squared minus 2x minus 24. And so we had our useful information. That was like the fact that -3 is a 0. That's like the fact that +4 is a 0. And we have transformed that into who even knows what's going on. Okay. Now we are doing this with a very specific polynomial. Clearly this is a quadratic that we are working with. So we could label these as like the A, B, and the C. I don't want to label these as A, B, and C though. I want to kind of keep this in our polynomial kind of terms or polynomial letterings. To that end, for our like polynomial function, what is 2 here? Thinking we had like that whole string of like coefficients and powers of x and all that. And so for this particular polynomial, what would we call 2? A sub what? A sub, say again? A sub n, fantastic. So A sub n was like that leading coefficient that we saw. So that's like the coefficient that is attached to the highest power. If 2 is A sub n, then what is this -24 going to be? A sub what? Remember the index 1 kind of tells us like where in our function it goes, but it also tells us how many x's are attached. And so for our first term, we have n x's attached. That's the largest number, the degree of our polynomial. How many x's are attached to this -24? None, so it would be A sub a sub 0. 0x is attached, so we'd have a sub 0. Right? Recall our polynomial a sub n x to the n, a sub n minus 1, x to the n minus 1, a sub 1, x to the 1, a sub 0. So this final kind of constant term here, we call a sub 0, just to kind of denote there's 0x's attached. Okay. Where did this a sub 0 come from? Where did negative 24 come from in particular? How did we get negative 24? Again? Okay, so 2 being distributed, hitting that negative 12. Where did the negative 12 come from? Positive 3, negative 4, which are our, there are zeros. So this negative 24 is a combination of this 2. What did we just say this 2 is? This is a sub n. So it's a sub n times the product of all of our zeros. Okay, so we can write that out. We could say a sub 0 is equal to, we're saying a sub n times, in this case, our 2 zeros being multiplied together, which would be like that negative, in this case, it's positive 3, negative 4. It's like the opposite of the 2 zeros, right? But we could think of it as like this generic k sub 1 times k sub 2. Right? First 0 being k sub 1, second 0 being. And we could imagine a higher degree polynomial, a polynomial with more zeros, where again, this a sub 0 term is still just going to be the product of all of the zeros and then whatever coefficient is sitting out in front, whatever the value of a sub n is. Right? So if I like added like an x plus 2 out here, then I would multiply this negative 24 by 2 and then multiply it by 2 again. And so what we have is getting really close to taking useless information and getting at the information that we actually want, these values of k here. Okay. Do we just, though, have the values of k? Like, have we fully isolated these? Is there something kind of muddying the waters? So is a sub 0 just the product of our, this is feeling very redundant, just the product of our zeros? No, there's something else there. What else is there? That a sub n, that initial term. So if our goal is to get at the useful information, the zeros of our polynomial, what should we do to both sides of the equation here? Divide both sides by a sub n. Fantastic. So a sub 0 divided by a sub n is going to be what? It is going to be the product of our zeros. Okay, so we're taking a bunch of zeros, we're multiplying them all together. And notice here, a sub 0 is going to account for the product of all of our numerators. And a sub n is going to account for the product of all of our denominators. This is the rational zero theorem. It's the idea that if our zero that we are thinking about is a rational number, then its numerator contributes to a sub 0, and its denominator contributes to a sub n. Another way to say that, and the more useful way to say that, is with how we are actually going to frame the rational zero theorem, which is that all rational zeros can be written as plus or minus P over Q. Thank you. Thank you. Thank you so much. Fantastic. Cool. All right. Plus or minus. Why do we have this plus or minus here? When we are multiplying all of our zeros together, so when we were doing this kind of product, would I have gotten a different value for a sub 0 if my 3 had been negative and my 4 had been positive? No. If I switched around the pluses or minuses, I lose that information when I actually do the multiplication. If we imagine multiplying like 6 or 7 numbers, some of which are positive, some of which are negative, it's going to be really hard to tell which ones contributed the positives, which ones contributed the minuses. Not only is it hard to tell, it's going to be impossible for us to tell which ones are positive, which ones are negative. And so to this end, we account for both the positive and the negative kind of combinations of P over Q. All right. So these are our zeros. They are contributing to our a sub 0. They are contributing to the a sub n. Where is the numerator of our 0 going to go? Is it going to go to a sub 0 or a sub n? It's going to a sub 0. And so P is a factor of a sub 0. And where is the Q going? Where is the denominator going? That's going to a sub n. And so Q is a factor of a sub n. All right. I've always found this a little bit intuitive before I actually sat down and tried to work out why this is the case, which is what we just did together. But again, this idea of that a sub 0 term, that last term there, is almost the product of all of our zeros, except we need to divide out a sub n. So once we divide out a sub n, then we end up with the product of all of our zeros. And so to that end, the numerators of our zeros contribute to a sub 0. The denominators of our zeros contribute to a sub n. What this gives us is like a really bad treasure map of finding zeros. So this is telling us that all possible rational zeros can be written in this form. And it doesn't tell us which ones are actually the zeros or how many of these are actually going to be zeros or things like that. It just says if you have a rational zero, then it has to be one of the things that can look like this. All right. So let's take a look. I'm going to take a look at example 3a here. We are given a polynomial. This is x to the fourth minus 9x squared plus 14. And we are trying to list, it says all possible zeros, all possible rational zeros for this particular polynomial. To that end, we need to figure out every single possible combination of P over Q. Right? This can get pretty long. I've kept these examples pretty short, but this can get fairly long. Let's go ahead and say, if I need to figure out P and Q, the possible values of P and Q, I need to know what A sub 0 is, and I need to know what A sub n is. So what is our value here of A sub 0, for example, A? 14, fantastic. And then what is our value for A sub n? 1, very good. If A sub 0 is 14, what could P be? What are the possible factors of 14? 7 and 2 and 14 and 1. Very good. I'm going to write that as 1, 2, 7, and 14. These are the possible values for P. And then if A sub n is 1, what could Q be? Just 1. Okay. Yes, Bill.
So we've always, is A always going to be the last?
A of 0 is always that last coefficient. It's whatever doesn't have an x attached to it.
A of n is always going to be
The first one.
Okay.
Yeah, I wouldn't give you one that's like tricky where like I swapped like the x to the 4th and the x to the 6th term, but it's technically A sub n is the one that's attached to the x that has the highest power, which should be the one that comes out in front, Yeah.
I'm sorry, but can I get like a little small, not rundown, but on what like A to the sub 0 and Q are?
So A sub 0 is the final term here of our polynomial. So A sub 0 in this case is this plus 14. That's just the constant term. A sub n is the coefficient that sits in front of our polynomial. In this case, there isn't one, so it's 1. P is all of the factors of A sub 0. So all the possible factors. In this case, 14 is divisible by 1. It's divisible by 2, it's divisible by 7, it's divisible by 14. So there are 4 possible values of P. And then Q, same thing for A sub n. So Q is all the possible factors. In this case, 1 is only divisible by 1. So that's all we're kind of saddled with.
All right, so the 2 A's are like the actual numbers, and
and then the P is like the pieces of the last number, and the Q is the pieces of the first number. Yeah, the factors of the first and last number. Yeah. Okay, and we are looking for every possible combination of P over Q, and we don't care if it's positive or negative. So all of the possible plus or minus P over Qs are going to be plus or minus 1 over 1. You don't have to write this as 1 over 1. It'd probably be better form to write this as just 1. I like showing you that this is P over Q, so that we like know what my value of Q is that I'm using. All right, so plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 7 over 1, and plus or minus 14 over 1. No, you don't. I'm just doing that again to show you the value of Q that I'm using. Again, it'd be better form to say probably plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. This is just so that we can see that it's coming from this value. So we don't like forget that it's there. Yes, see. Yeah.
Would you have to all of those over?
Yeah. We'll look at B here, where the number of factors, still 3 prime number, not too bad. But yes, the number of possible combinations does get very large very quickly, which is kind of the downside of this. And the other downside is 1 does not have very many factors. 14 also doesn't have that many factors, right? It's really only divisible by 2 and 7. I mean, it has 4, but like 4 is pretty low in terms of like the number of possible factors that you can have. It doesn't take much to break this apart into its primes. And how many zeros, how many possible zeros did these 2 things that don't really give us many options, how many zeros did it generate? 4. Looks like 4, but what is it actually? 8. It's actually 8. because every single zero that we see here is either the positive version of the zero or the negative version of the zero. And so we could see this getting out of hand very, very quickly. And all this is saying is that these are where the zeros might be. If there is a rational zero, this is where they would live. It's possible that there are no rational zeros. Maybe our zeros are all like pi or e, or they're all like complex numbers, and none of them actually work out to be that. So then we have our list of possible zeros. Our goal is ultimately our goal of finding all of the zeros. What would we do to check to see if the zero that we're looking at is in fact a zero or if it's just nothing? That's probably the easiest way to just check to see, is what I'm looking at a zero? I would probably just plug it in for x. Last year when I was teaching this, I said that what you should do is you should divide the polynomial. So if I want to check 1, you would divide the polynomial by x minus 1, and then you'd have like 8 different like long division problems to do to check to see if any of these are zeros that work. That's bogus. I just wasn't thinking well. Yeah, absolutely. The easiest thing to do is plug in the value and see, does it work as a zero? That's still 8 values that we are needing to check to see is what we are looking at a zero. And actually, I'm pretty sure for this one, you could plug in all 8 and none of them work. Because I don't think this one has rational zeros. We could check it pretty quickly. This is y equals x to the 4th minus, 9x squared plus 14. Oh, no, it does have zeros. But they might not be rational zeros, I think is the problem. So this one does, in fact, have zeros. They just might not be fractions. They might not be particularly nice numbers. And I actually don't think that they are. I don't think that these work out to be very kind. And so we have this kind of problem of like, okay, this is cool. We could now find all of the zeros from our own. It's still pretty difficult. And as we'll see in an example here, that number of zeros can very quickly get out of hand. So for instance, let's take a look at B. Let's do the exact same thing. We're just trying to list all possible rational zeros here. What is our value of a sub 0? And what is our value of a sub n? So a sub 0 is 10, and then Gabby? Perfect. A sub n is 3. So what are our possible values for P here? 1, 2, 5, and 10. And then what are our possible values for Q here? And 1. Always going to be 1. Okay. So again, really not that many factors still, right? These numbers are still not super divisible. Nothing like too outrageous. And we're going to see that there are a lot of zeros for us to check from these not very many factors. There are a lot of combinations of this. The way I kind of like to do it is I like to do all of my p's divided by one of the q's, and then do all of my p's divided by the next one, just to kind of keep track in my head that like I've done what I want to actually do. But however you want to do it is totally fine. But I'm going to set this up that all of our plus or minus p over q's are equal to, again, plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 5 over 1, 10 over 1. And then for our other value of q, we also need to check what's going on at 1 over 3, 2 over 3, 5 over 3, and 10 over 3. That is 16 possible values of 0 that we have in front of us, which is a lot to check. Okay, so we now have self-sufficiency because these are the realistic, these are the reasonable zeros. These are the rational zeros. These are the nice ones that we have a shot at finding. still sucks. Still not great. And so to that end, I will either be giving you a relatively few number of zeros to check. So like I might ask you, like I'd say 8 is probably the upper limit of what I would ask you to like manually check. Even then, that's probably a lot compared to what I might ask you to check. So like 8 is maybe the upper limit, but like I'm not asking you to plug in 16 values in text here. What you might be reasonably expected to do is to list all of the possible zeros, and then maybe I give you a hint and say, oh, by the way, 1 is one of those zeros that we actually can use. Go ahead and figure out by long division the other ones that ones. You're generally not going to have to take a polynomial, factor it all from scratch, but we now have the ability to do so. It would be a long, laborious process. I am not here to make you do a bunch of busy work, at least that's not my intent. And so, generally speaking, I will not be asking you to plug in 16 different values into your function. It would either be that, or you would like plug it into a graphing utility, find one good value of 0, and then do the division of all the others, or do the division to find all the others, right? Either way, though, we do now have this ability to generate all of our possible, again, rational zeros, which is helpful. So we have gone from now very little self-sufficiency, where like I was having to factor your polynomials for you, and then we worked our way up a little bit. Now we can, in fact, fully factor our polynomials if we are given certain factors, if we're given that 1 is a 0 or the 3 is a 0, whatever. And now we have full self-sufficiency, assuming that there are rational zeros to be able to find, which is a little bit of an assumption that we are making here. But if there are, then they're all in this form right here. How does self-sufficiency feel? You feel accomplished? Accomplished mathematicians? Like, I can now tackle any polynomial with an excessive amount of work. An excessive amount of pain and suffering, and I can get through any polynomial. And that certainly is now a skill that we have. Yes, Simran. So is there like a way to like figure out where the possible roots could be, like for like real values or for like complex values? We're going to look at complex values here in a second. But generally, no, we don't really have like a good way to figure out like what the possible real zeros could be. The real numbers are just so odd. They're so weird and difficult to kind of like pin down. We don't even have like a good way to represent real numbers, let alone like figure out like the possible roots. So unfortunately, this is as good as we get. We just kind of hope that in fact there is a rational zero that we can kind of like hook and work from there. And for the examples that I will give, there certainly will be one. But yes, it's a very limited self-sufficiency, isn't it? We certainly still would not be able to deal with a polynomial that just has complex roots, and if it has like weird real roots as well, that could certainly be problematic as well, for sure. Although actually, to both of those possibilities, the same answer, the same solution exists, which is kind of nice. Which is that if we know one of them, that we can figure out very easily the other. Yeah.
If we figured out that there could be like 16 different possible zeros,
yeah.
What was the plugging in the equation for?
So these are the possible zeros. If we wanted to figure out which ones are actually 0, we would pick these values, plug them in for x, and see which ones gave us 0. So for instance, if I plugged in positive 1 into x, I would get 3 times 1 minus 4 times 1, negative 1, plus 11 plus 10, that's not going to be 0, that's going to be like 20. So that one wouldn't actually be a 0.
On the actual graph, we wouldn't see how many times we counted a 0 as long as there is a 0.
Yeah, so like these won't show up when I actually plug in my graph. only the ones that are actually zeros would show up. So the possible zeros you can't tell from a graph. You can only tell the actual zeros from the graph, which is good because that's what we actually care about is the actual zeros. Yeah. This is like a way without graphing to narrow down what those actual zeros could be. So we're not just like randomly guessing numbers and hoping that that one sticks.
Because on the first one, A, when you plugged in like the normal base value,
Yeah.
using 1, but just instead of putting X.
Yeah.
I saw that there were like 4 of them, even though there are 8 possible ones. So I'm like, if we tried the other ones, wouldn't it just give us way too many possible zeros? Then.
Oh, you mean like for the other numbers here, like for the -9 and all that, or?
Yeah, I guess.
So the only thing that this theorem cares about is what's going on at the front of our polynomial and what's going on at the end.
Oh, no,
the noise doesn't
I wasn't
matter.
talking about that. It's
Okay.
just if you replace the X with 1.
Oh, so like for plugging in the X as 1.
Okay, whatever.
Basically, you won't actually need to plug in to check. You'll go to the graph and then you'll see, okay, of these possible zeros, 1 is a 0. So I'll use 1 as like my division, my thing for the long division. Would it be helpful to see that in action? We can maybe look at that. We'll look at maybe an example where we do it all from scratch. We'll do one for bell work tomorrow, where we can kind of see it all from scratch kind of play out. Okay. So we have a lot of self-sufficiency now. What we are going to do here, we've got a couple of more things to wrap up. We're going to address Sumaran's question of what do we do if there are complex zeros? What do we do if there aren't? We're not actually going to talk about real zeros, but the answer is the same actually, which is kind of cool. First thing is something that we have really been kind of assuming is true. But now we're going to conclusively say that it is in fact true. This is the fundamental theorem of algebra, which says if I have a polynomial p of x, I can write it out as the product of all of its zeros. Which is like the thing that we have been doing this entire time, right? Now, interesting thing to note here is that these values of k are complex numbers. So yes, the real values, the rational values that we have been using up until now will continue to show up. But it is certainly possible that we end up with complex values. The linear factorization theorem then adds to this. I used to kind of teach this as like a bundle. It's kind of all the fundamental theorem of algebra. It's very easy to go from the fundamental theorem of algebra to the linear factorization theorem. It talks about how many of these little roots that we get from a particular polynomial, but this is kind of, I think, fairly self-evident. If I have like x to the 6th plus 5x to the 4th minus 7x cubed plus 12x squared minus 11, how many of these little root things should I end up with? I should end up with 6, right? Because if I have more than 6, when I multiply them all together, I'm going to end up with x to the power that is greater than 6. And if I have less than 6, then when I multiply them all together, I'm not ever going to hit x to the 6th. And so I have to have exactly 6 of these roots. Right? So the linear factorization theorem tells us that there are n roots, where again, n is just the degree of our polynomial. So if I have a 5th degree polynomial, we'll have 5 roots. If I have a 107th degree polynomial, then there are 107 roots. It's just whatever the power of x is here, we have that many roots. Some of them might be repeated. That's okay. We can actually make a note here that that's like including repeated roots. Right, so like our multiplicity doesn't like mess anything up, but this is very simply just saying power of 6, 6 roots. Okay. One final thing that we are going to talk about is this whole like presence of imaginary numbers. Because I've been saying that we could have complex solutions, that we could have complex roots. But when we look at our polynomials, for instance, this could have roots that have I in them. But when we look at the polynomial itself, do we see i's in the coefficient? No. How could that be? How could it be that we have this be divisible by, say, like some kind of I, but then not see those imaginary numbers in the coefficients? We've actually already looked at a case where we've started with a complex number and then like tried to turn it into a real number. For instance, if I start with, say, like 5 plus 2i, what do I need to multiply this by in order to turn it into a real number, in order to get rid of the i's? 5 minus 2i, very good. And what was this called? Yeah, exactly. This was the complex conjugate. All right. And so in order for us to have these complex values as factors and not see any i's in our coefficients, if, for instance, I know that 5 plus 2i is a 0 of my polynomial, then I get for free that its conjugate must also be a 0. Just can say that instantly. All right. So, complex conjugate theorem states that if a plus bi is a 0 for a polynomial with real coefficients, so we don't see any i's, then a minus bi must also be a 0. It's the only way to not have i's show up in our coefficients. Similarly, there's like, we could generalize this to just the conjugate theorem probably, where we could say something like if 2 plus the square root of 5 is a 0, and I wanted to, and I don't see any square roots or anything in my like final coefficients, then 2 minus the square root of 5 must also be a 0. So kind of similarly, we deal with these complex numbers as we do these like weird square root 0 real numbers, which is to say that if we know that one complex number is there, then its conjugate must also be there. If a real number is here, then its conjugate must also be there. Which is just extra to kind of talk to Sumiron's point of how do we deal with those real numbers similarly to the complex numbers. Okay, so let's see this in action here. One final example. This is kind of bringing a lot together here. In this case, we are trying to write the equation for a polynomial given certain criteria. So for instance, for A, we are trying to write the 4th degree polynomial. If we are a 4th degree polynomial, how many zeros should we have? 4. We are given 3 of those zeros. We are told that -3 is 1, 2 is 1, and then I is 1. Now, according to our complex conjugate theorem, if I is a 0, what else has to be a 0? -I also has to be a 0, exactly. And so we can take this polynomial p of x, and we can write it as some coefficient, we'll call it a sub n, times x minus -3, well, that's really going to be +3, times x minus 2 times x minus I, and then times x minus negative I, which is going to, again, be x plus I. So this coming from the conjugate. Okay. So the only thing that we're missing here is what? All we're missing here is this value of a sub n. So the -2, and so we've got this. Yeah. So we're going to use this f of -2 here to find the value of a sub n. So we've got one more piece of information here that we are going to incorporate. Before we plug in -2 to find a sub n, I'm going to clean this up a little bit. It's kind of hard to deal with i's, and so before things get super complicated, I'm actually going to do out this multiplication. You could do the Punnett square. You could remember that a plus bi times a minus bi gives you a squared plus b squared. However you want to do it is totally fine. But when we clean this up a little bit, when we do our, say, our Punnett square, I get x squared minus ix plus ix, and then negative I squared. And what is negative I squared? Positive 1. Negative ix and positive ix are going to cancel. And I am going to end up with, again, this a sub n. Nothing's happened here. Nothing's happened here. But now this product, x squared plus 1. So all of our i's have vanished. They're all gone. They're still kind of there as roots, but we don't see them in the coefficients anymore. Okay, and so to find that missing value of a, that missing coefficient, we're going to do exactly what Kenan was saying here. We are plugging in that -2 for x and setting it equal to 100.
The negative I squared.
Negative I squared turned into positive 1. So I squared is -1, negative 1 is positive 1. Yeah. And so plugging in -2, I get that 100 is equal to a sub n times -2 plus 3 times -2 minus 2 times -2 squared plus 1. -2 plus 3 is just 1. -2 minus 2 is -4. -2 squared is 4, plus 1 is 5. This tells me that 100 is equal to -20 a sub n. Dividing both sides by -20, I get that this value out here, out in front, is -5. And so we can kind of go back into our original function here. I don't really care where you do it. I'll do it up here. And we're going to say, well, we now know that a sub n is -5. And so this would be our full polynomial. Questions here? All right, let's take about 5-10 minutes. Take a stab at B. So in this case, looking for the third degree polynomial. Third degree means how many zeros? 3 zeros. I've supplied 2 of those zeros. You'll use the complex conjugate theorem to figure out what is that other kind of missing 0, and then exact same process for finding that coefficient that lives out in front of plugging in the value of 1 setting it equal to. Take a minute to take a stab at those. Yes.
So I've actually have a question.
Yeah, you're totally.
So, I was looking over for the 2.4
Yeah.
pieces. Something it had to do with long division. It was called like
Synthetic division.
Yeah, I don't remember seeing
So
that.
yeah, we didn't talk about synthetic division. If you know how to do synthetic division, I don't have a problem with it. But everywhere you can do synthetic division, you can also do long division. So
I had to learn.
yeah, whichever one you prefer, you can use. I prefer long division. I think that it's very clear kind of what your steps are and like why you do them.
I never learned long division.
Okay, so whichever one you feel most comfortable with, as long as you feel good about them, then you can
get the same number.
You get the same thing either way. Yeah. It's ultimately the same process. Synthetic division just kind of gets rid of all the x's, which is fine, and you do the same thing. But whichever one you're most comfortable with, I'm fine with. That looks perfect. Perfect. Negative 2i times positive 2i. Is that going to give us a negative 2, negative 4? I agree. And then what is I squared? Negative 1, so that'll turn this minus 2a. And then the I squared will just go away. Perfect. Yeah, that way we just don't have any i's for when we actually plug in 1. We're like, all happy and good to go. What is 1 plus 4? Otherwise, looks great. Perfect. Sept. Okay. Perfect. You multiply 2i and negative 2i. 2 times negative 2, that should give us a 4i squared, negative 4i squared, which has into that one. Yeah. So if I is a 0, then negative I will also be 0. Yeah, so that's the complex conjugate. So in this case, negative 2i is a 0. So what's the conjugate Yeah, no. So the root would be x plus 2i would be for that 0. So then x minus 2i must also be a root. Yeah. Yeah, absolutely. Yeah, for sure. Yeah, and so then dividing those by 4 negative 20, get that value base of that. That's perfect.
Is it the same as rational consecutive?
Yeah, kind of, it's very similar. Yeah, it's very similar, where the idea is like, where does this like last kind of come from? And yeah, it comes from that kind of multiplication.
But then we only get 2 roots here.
Yeah, because this is a secondary polynomial, right?
Oh, yeah.
Yeah. Yeah, so we would only expect 2 roots.
So this is to find the roots for this.
So this one actually, I don't think this one has very nice roots. I think the roots end up actually being pretty disgusting. And we could try it. For instance, we could write out this one as, so like if I wanted to like factor this, what I would do is minus 9 plus 14. I would turn this into a quadratic. So like I would substitute x squared. I would say that let's let u, a dummy variable, equal x squared. And so rewrite that quadratic as u squared minus 9u plus 14. And now this is something I can factor. So like what are two numbers that multiply to make positive 14 and add to make negative 9? Two numbers that multiply to make negative 7 and negative 2. And so we would get like u minus 7 times u minus 2. And we would get, but it's not really u, right? It's actually x squared. And so what are the zeros that we get? Well, what we really get is x plus root 7 times x minus root 7 times x plus root 2 times x minus root 2, which are none of the zeros that we looked at with the rational zero theorem, because none of those are rational numbers, they're all real numbers. But this is kind of to what we were talking about earlier, where notice that the conjugates of each are here. So the fact that positive root 2 is 0 means that negative root 2 is 0. The fact that positive root 7 is 0 means that negative root 7 is 0. And so if I gave you like one of these, you probably actually could find all of the other ones using this idea of conjugates. Which would make for a really fun bell work to do tomorrow. Okay, so let's take a quick look at B here. Just as far as like the shell of our setup, what is our polynomial going to look like? Some kind of generic a sub n. If 5 is a 0, then we know x minus 5 is a root. If negative 2i is a 0, then x plus 2i is a root. And then if negative 2i is a 0, then what else must be a 0? Positive 2i must also then be a 0, which is going to make the root x minus 2i. Doing out that multiplication, you can make the Punnett square or do the foiling or whatever. Either way, you should get a sub n times x minus 5 times x squared plus 4. And plugging in 1, I get that 10 is equal to a sub n times 1 minus 5 times 1 squared plus 4. That tells me that 10 is equal to negative 20 a sub n, and that a sub n is equal to negative 1/2. So we'll go back in here. And we'll say that this is really negative 1/2. Questions with our anything from 2-5. So this could be factor theorem, remainder theorem, rational zero theorem, complex conjugate theorem, all of those. I will give that back. We'll see. We're going to do something with that. So we are, if you guys would actually take out your laptops, go to the Unit 2 folder in Schoology. There is an exit ticket for today. I believe today's the 7th, so I hopefully labeled that correctly. But if you guys would take a moment to fill that out. Done a couple of these kind of similar ones here as we have kind of gone. But really just kind of highlighting what are some of the things that we're feeling good about going into the quiz that we have, and then what are some things that like we would like to maybe see some practice with, all that good stuff. Okay, Teams.